Okay, so I'm not going to be around on January 14th. I have to do a meeting or something like that. So this video is going to be something of a substitute. And maybe there will be one or two more videos in addition to this one. Um, yeah, to be a substitute for class on January 14th. Recall that yesterday we were talking about the exponential function, e to the z. And this is really our first brush, other than with polynomials, in thinking about a complex function, a function which eats a complex number and spits out a complex number. Recall that we defined that exponential function using the Taylor series. The Taylor series is something that you learned about in your calculus class and looks something like this, but there you probably wrote e to the x equals sum from n equals 0 to infinity of x to the n divided by n factorial, right? We are, by writing this z here, we are implicitly extending that definition from the real numbers to the complex numbers. And this is how we're going to define e to the z, where z now is a complex number, and e to the z is potentially also a complex number, right? Because we're taking powers of z, we're dividing by n factorial, and then we're adding up infinitely many of these terms. Um, I'm asserting, and I'm right, that this thing converges for all z in the complex plane. But maybe that notion of convergence is still a little bit murky or mysterious. And certainly we're going to get into the world of power series in defining what are called holomorphic functions soon enough. We also could define cosine of z and sine of z in the same way, that is to say, via their power series representations. And extending the power series representations from merely the real line to now the complex plane. Right? And that's sort of what we've done here. And something beautiful happens when you do that. There emerges a beautiful relationship between e to the z, cosine z, and sine of z called Euler's identity. And here's Euler's identity in all of its glory. One of the most beautiful identities, perhaps the most beautiful identity in all of mathematics. There it is. E to the iz is equal to cosine z plus I sine z. Now I want to emphasize this holds for all z, all complex z. So in particular, don't get it twisted. We can't use our intuitions about these functions like cosine of z and sine of z that we earned from our understanding of these as geometric things about when z is a real number. We need to learn more about how cosine of z and sine of z behave when z is a complex number. Okay. However, let's imagine a situation where z here is a real number, and that's what I've done here. I'm asking you to imagine that z is real. Did I just say? I think I think I said it right, but I'm not totally certain. Okay, so just imagine z is real, please. All right. Then what can we say about the modulus of e to the iz? Well, by the Euler's identity that we just established, e to the iz is cosine z plus I sine z. And so the modulus of e to the iz is the modulus of cosine z plus I sine z. But now, crucially, if z is real, then this cosine of z and this I sine z here are real numbers. So this is the honest to goodness rectangular form for a complex number. We know how to define the modulus of that. You just take the square of the real part and add to that the square of the uh, uh, um, imaginary part. Oh, but I'm realizing that I think I forgot a square root here. This ends up being, of course, the square root of this, which is the square root of 1, which is 1. And it doesn't matter that I left off the square root. There are still true statements, but this is more in the spirit of sort of easier to follow, let's say. Yeah? Okay. Okay, so what is this saying? This is saying that if z is a real number, then e to the iz ends up having modulus 1. What does it mean to have modulus 1? It means that your distance from the origin is 1. And what is another way of saying that your distance from the origin is 1? Well, that says that you live on the unit circle. So here's the idea that I to sort of begin to visualize what's happening. I'm going to think about two copies of the complex plane. One where z lives, and one which is going to track e to the z. Okay, so here's one complex plane, and then I'll draw another over here. And the thing that's going to link these things is e to the z. All right. Now, I want to use the insight that I just developed up here to understanding something about this mapping between two complex planes. Yeah. In particular, if z is real, then do you notice that iz is some number along the imaginary axis? So I want to focus for a moment on the imaginary axis of the complex plane here. That's the vertical axis, yeah? Okay, so maybe a dynamic way for you to imagine this is to imagine that z is a particle, that you have a particle sitting in this left-hand complex plane. And that particle can move about, and there's going to be a corresponding particle over here in the right-hand complex plane, which will also move about under the transformation e to the z. So first, let's think about very well-regulated movements, okay? So let's imagine that, in particular, this particle here moves along, travels along the imaginary axis upward, starting at the origin and then traveling upward. If z is 0, then you can see here from e to the iz being cosine z plus I sine z that we end up at the complex number 1, z is 0, plus I times 0. Or in other words, 1 plus 0, I. In other words, 1. Okay, so we end up here. I'm going to imagine that's 1 right there. This is, if the particle starts out here, under this mapping e to the z, it ends up there. All right? And now, again, imagine it travels upward. Then what's happening is that this angle, this z here, is increasing. It's getting larger, both here and in the imaginary part. And so what we're going to see is us revolving around the unit circle. Something like this. Okay? Revolving around the unit circle. Okay, neat. In other words, what I'm saying to you here is that as we travel upward along this imaginary axis in the z-plane, over here we are traveling around this unit circle here in a counterclockwise fashion. And as we go from 0, if we start out at 0 and we go up to, let's say, 2 pi, we will have traversed this unit circle 1 full revolution. Does that make sense? And as we move past 2 pi I, we're going to travel around this unit circle even more times. You can also imagine traveling in the other direction. Like, let's say we started out at 0 and we traveled downward into the negative imaginary axis. Well, then we are going to go around this unit circle in the clockwise orientation. And again, we're going to wrap around this thing infinitely many times as we are traveling down. Yeah, I messed it up. But you get the picture, I hope. Okay? So this green line, this imaginary axis, wraps around the unit circle infinitely many times. Okay, cool. Let me just remind you of something that you learned about in at some point in your life. You learned about polar coordinates. Okay, so just a quick reminder. You wrote down pairs r comma theta, right? This is a point in R2. The point. in the plane whose distance from the origin is r, and which, I'm going to say it like this, which makes an angle of theta with respect to the positive x-axis. Okay? It makes an angle of theta with respect to the positive x-axis. So this is just a different coordinate system, but sometimes it's very, very useful to have a different way of representing points in the plane. The one that you're probably much more accustomed to is, of course, the rectangular coordinate system, x comma y, where you're given those two coordinates, you can locate points in the plane. Well, with polar coordinate system, you're given numbers r comma theta, and they have a different geometric meaning, but they do just as good of a job as locating points in the plane. All right, that's polar coordinates. All right, so now we want to apply the polar coordinate idea to the complex plane. So let's apply this idea to the complex plane C. All right, so let's suppose that we have a complex number. Let's call it z. Z is going to be a complex number. And let's let r be the modulus of z. That's, after all, the distance of z to the origin by definition of modulus. So r is going to be the modulus of z. Okay. Then notice that if we take the modulus of z divided by the modulus, so the feeling that you should feel here is like, this is me normalizing z. This is me like making z unit length by dividing z by its modulus. Oh, I guess we need to assume here z is not 0. Yeah, so let's assume z is not 0. Because if z was 0, I'd be dividing by 0 here, and that seems like a bad thing to happen. All right? But in particular, will you believe me that this is unit length? In other words, this is a point on the unit circle. And we just got done saying that points on the unit circle are of the form e to the iz, for some real z. And in fact, that z tells you about the angle that the point of the point on the unit circle, that angle words. If you take the ray that emanates from the origin and passes through that point on the unit circle, you measure the angle that ray makes with the positive x-axis, and you get that that's the value of z. Right? That angle. Okay, so then using that here, we can say z over the modulus of z is equal to e to the I theta, where theta is, again, has the interpretation that we had above. It's the angle that this point z makes with the positive x-axis. Okay? And very clearly now, if r is the modulus of z and z over the absolute value of, the modulus of z is going to be e to the I theta, then what we can do is just write z as r times e to the I theta. This is sometimes called the polar form of z. Let me write that a little bit nicer. Okay? Times e to the I theta. R here is a real number. In fact, it's a positive real number. Yeah? And I guess it could be 0 if you want to allow 0 into your life. And then e to the I theta is some point, some complex number which lives on the unit circle. Okay, that's enough for this video. I'll continue this in another video. All right.